Well, this lecture is based on two topics. One, time independent Schrodinger equation, and the another is the Gaussian wave packet as a solution of free particle. So let us start from the time independent Schrodinger equation. We know that the Schrodinger equation, time dependent Schrodinger equation, and in our previous class we have discussed about this. Here psi is the wave function which is dependent on x, y, z and t coordinate, that is time and position, and here v is the potential within which the particle is moving, and in general you can write the potential as both function of position and time. So r comma t you can write, but here from the beginning I have assumed that potential is not explicitly function of time. So here you can proceed by using the actually I have no, actually not that, yes, here now using the separation of method of separation of variable, you can write psi as a product of the position and time functions, and let us put them into the Schrodinger equation, because easily you can write del psi del t is equal to what? Phi will be constant, so df dt. So in the left hand side of the time dependent Schrodinger equation you can put this, and similarly del 2 psi del x2 you can write f into d2 phi dx2. So at the right hand side you can use this. So this will lead you into this form where the left hand side you can see is a function of time. It is a function of time, but the right hand side is a function of the position. So if they are equal, so they must be equal to some constant which is called separation constant E, and here we can divide this equation into two parts. I h cut 1 by f df dt is equal to E, so it is written over here, and if you integrate this you can easily get left hand side will be log of f and the right hand side will be minus I e into t by h cut. So f will be exponential of minus I e t by h cut. We are avoiding the integration constant. We assume that integration constant is 1, and the another equation which is a function of r is equal to the separation variable E give you this equation, this famous equation, and here you can relate that this operator minus h cut square by 2m del square plus Vr is the Hamiltonian operator. We have discussed this one. So the left hand side in the operator form can be written as H operator operating on phi, and the right hand side is E phi. So this is an eigenvalue equation, and E is the eigenvalue corresponding to the Hamiltonian operator. So the E is called the energy eigenvalue. Okay, yes, here it is written energy eigenvalues. So E, the separation constant, has a physical significance, that is, it is an energy, and it is coming from the eigenvalue equation of Hamiltonian, so it is energy eigenvalue. So this equation is called the time independent Schrodinger equation. H phi is equal to E phi, or in the form of operator, so in explicit form you can write this minus h cut square by 2m grad square phi plus Vr phi is equal to E phi. here you can see the separation of variable is possible because of the potential which is independent of time. If it is not independent of time, you cannot separate the time dependent Schrodinger equation into two half, one time dependent and the another is time independent, because if v is a function of r and t, you cannot write the right hand side equation as a function of r only. So the method of separation variable will fail, and you cannot get this time independent equation. So time independent equation is the result of the fact that the potential is independent of time. Now the total solution you can write. The time part we have found it, e to the power minus I by h cut et, and is a scalar, and into multiplied by phi r. Phi r we have to find out because we don't know about the potential Vr, and if you know the potential Vr, then you can solve this differential second order differential equation to find the phi, that is the time independent wave function. So here the wave function is written as it was. The interesting fact that the probability density, that is mod psi square, is equal to psi star psi. So this time part will vanish, so the results in mod phi square, that is independent of time. This kind of solution, that is psi, will be called stationary, because for this wave function psi is a total wave function of the system, and it is dependent on time also, but the probability density is independent of time. That is, with irrespective of time, the probability density will only dependent on the position of the particle. So this kind of solution, that is psi, is called the stationary state solution. Okay, the states of a quantum mechanical system for which the probability density doesn't depend on time are called the stationary states. But as I have talked earlier, that is the Schrodinger equation, the solution of the Schrodinger equation should be written in terms of the linear superposition theorem, because many solutions can be possible for a particular potential. So superposition principle leads you to the general solution psi RT as a superposition of all those psi, that is phi r into e to the power minus I by h cut et, those taken into the linear superposition, where C is the linear superposition coefficient, that is the expansion coefficient you can say, and here you can see the explicit form of the expansion. But here psi is the general solution of the Schrodinger equation, time dependent Schrodinger equation, and you can see very easily that psi is non-stationary. We can deduce it very easily, that is mod psi square is the double sum over Cij or Ci star, because Cj can be complex in general. So Cij, if you multiply two sums, these two sums are multiplied to each other, 1 over I and 1 over j, to give you the general form. So there will be phi I star and phi j into e to the power, here you can write I by h cut ei minus ej into t. So it is a function of time. So the probability density is function of time. So the psi, the general solution of the Schrodinger equation, is not a stationary one. but the particular solutions, because this one or this one or this one are stationary states, because for those cases the probability density for that particular state is not a function of time. So these are stationary, but total or general Schrodinger equation solution is not a stationary. So this concludes the topic of stationary state and the time independent Schrodinger equation. Next we are going to discuss the concept of wave packet in quantum mechanics. We have a primary idea on this, why wave packet is formed, but here in the light of the free particle we are going to see that in case of free particle the external force is 0, so the potential is 0, the particle is moving, and solely the particle has only the kinetic energy, so the energy of the particle is greater than 0, and you can write the time independent Schrodinger equation in one dimension. Obviously I am talking over here. So the one dimension Schrodinger equation, time independent Schrodinger equation, can be written like this, and here you can jumble up to get the famous SHM type equation, where k is the root under of 2me by h cut square, and the solution of this second order ordinary differential equation has two solutions, one e to the power ikx and another is e to the power minus ikx. So linear superposition, that is the general solution, will be a into e to the power ikx plus a minus e to the power minus ikx, and time, and the time part e to the power minus I omega t is there, where for the actual time dependent Schrodinger equation solution is written over here. Okay, it as a time as a time independent solution, here you can see it is phi x. So phi x can be written as a plus e to the power I kx plus a minus, a plus and a minus are the two arbitrary constants, and psi xt, it is a solution of time dependent Schrodinger equation, is a product of time independent part and the time dependent part, and we have found earlier that is time dependent part is e to the minus I omega t, where omega is equal to e by h cut. So it is written here, you can see, and now you can put in place of k p by h cut, because from the Broglie hypothesis you can write p is equal to h cut into k, because your k is nothing but the propagation constant, so 2 pi by lambda, so lambda is equal to h by p because of the Broglie hypothesis, so p by h cut will result in, so k is equal to p by h cut. You can put it and you can get this equation number 6. Now the first term, you can see the first term is the wave propagating, is a harmonic wave, or you can see the you can tell it at as the plane progressive wave, which is plane wave traveling into the positive x direction, and the second one is plane wave traveling in the negative x direction, and here a plus and a minus, or a plus square and a minus square, are the intensities of the waves. So those two waves are superposed. Okay, so this will give you the net solution of the Schrodinger equation, that is, a net matter wave is the superposition of two waves, one traveling into the positive x direction and the another is traveling into the negative x direction with same wavelength. Okay, so And another feature you can see here, that is there is no restriction on the particle, because the particle is under force free condition, that is a free particle. So the energy can be of any of the value, that is continuous energy spectrum will be observed. So E has no restriction on it, so E can be any value, so every continuous value is possible, so continuous energy will happen there. Now the problem looks like that it is very easy and we have solved the problem quite successfully, but at the same time some difficulties arises. The first difficulty is that the probability density corresponding to either solution, that is for the traveling wave along the positive x direction or the negative x direction, is the a square mod a square. So that is independent of time and position. So the particle, this is so the particle, you cannot say that the particle the position of the particle can be anywhere, because it is not a function of x, it is a constant. The probability density is constant. That means the probability of finding the particle in the range x to x plus dx is constant. So everywhere you can see the particle. So the position of particle is totally uncertain. So this is violated by Heisenberg uncertainty principle. And as we have discussed earlier also, that is Heisenberg uncertainty principle says if there is no uncertainty in the momentum, the position completely is uncertain, or energy is completely certain, then the time completely uncertain. So it is happening over here, because the probability is not dependent on the position and time. So the at any position and any time the probability of finding the particle is constant. That means that the particle can assume any position at a particular momentum. So the position of the particle is completely uncertain. Now move on to the second difficulty of the free particle solution. See, the wave is traveling with the speed omega by k, so you can write omega by h cut and divided by k. So h cut k is your p, so p is nothing but or you can write like this, h cut k by 2m. How you can substitute using E is what? E is p square by 2m. So p is equal to h cut k, so h cut square k square by 2m. So if you put E is equal to h cut square k square by 2m, so results in this formula, which is the phase velocity of the wave, that is the wave velocity. Now the particle velocity is p by m, that is momentum by mass, so h cut k by m. So h cut k by m, that is twice of the wave velocity. So particle is moving with the velocity which is twice of the wave. So wave is moving slower than the particle. And what wave? That wave which is describing the particle. So this is a fallacy. So wave, how wave gets slower or left behind the particle, where the wave indeed a representation of that particle. So this is a difficulty. And third one is also a crucial one, which is the if you use the solution for psi, which is a plus e to the power something plus a minus e to the power something I into something. So this is not normalizable. If you put the form of psi from this equation into the normalization condition, or mod psi square, yes, this one, if you use this psi, this one whole psi can be put that is equation 6, and you can see here. Yes, so the result will be infinity. Okay, so e to the power, you can see it very easily, or you can just put those solution, and you can readily obtain that integration minus infinity to plus infinity over dx, so result will be infinity. So the total probability is infinity. It is avoidable condition, because this condition should be avoided. So the wave function is not normalized, because you cannot find the a constant from this equation. So the natural question which arises, is there any way out of those problems? Answer is yes, and what saves us, that the Schrodinger equation is consistent with the linear superposition principle. So the solutions which we have got into the equation 6 can be summed up over the whole space to get the net solution as this form, which is called the wave packet. See, each of the solution, you already have got this result, e to the power I kx minus omega t, this kind of solution you got here, and now superpose those solutions or sum up those solutions for all possible values of k with a coefficient psi tilde k, psi tilde which is a function of k, and adding up means here the as the k is a continuous, because k is your related with the momentum, and momentum can take any value p by h cut. So momentum can be continuous, so k is a continuous. So k is a continuous which is a function of omega in general, that is dispersion relation, and this is not important here to discuss about this. Just keep in your mind that k is a continuous function, a continuous variable, and here the k e to the power I kx minus omega t is a plane wave solution, and those plane wave solutions are superposed to each other with different amplitude, where amplitude part is written as psi tilde k, and this one those solutions are summed up, and at the from minus infinity to plus infinity, and here the factor, just ignore this factor for the time being. Now what is the significance of psi tilde k? This is called, first of all I have to tell you that this psi is the general solution of the Schrodinger equation. In my previous lecture, where the time dependent Schrodinger equation has been set up, I have described in two methods. In one method I have reached the Schrodinger time dependent equation from the plane wave solution, and another is from this equation, which is the wave packet solution. And here you can also, by differentiating, you can satisfy the time dependent Schrodinger equation. So this is nothing new to you, but what is new is that what is psi k, you know this, because if you write this psi, you can see is a function of position and time, and if you put time is equal to 0, that is psi x0, you can write this equation like this: minus infinity to plus infinity psi tilde k e to the power I kx dk. So this is nothing but the Fourier transform equation, where the Fourier transform is psi tilde k, which is given by this equation. So psi tilde k is your psi x0 e to the power minus I k ax dx. Okay, and by the factor 1 by root 2 pi is written outside the integral. So this is, so psi tilde k has a physical significance that it is the Fourier transform of the time independent solution of the Schrodinger equation. Okay, so Fourier transform of a solution, Fourier transform of a wave function, or you can say it is the wave function in the momentum space because it is a function of k. So two representations, one position representation, this is position representation, and this one is the momentum representation wave function of the Schrodinger equation. So if you take those two forms, that is psi xt or psi x0 and psi tilde k, you can solve those problems. How? You can see that is actually this will be more clearer into my next topic, where the wave packet has some definite shape, and here it is general talk I am going to tell you that the wave packet is what is the graphical picture of this psi. Okay, so let us go to that picture. Yes, this is a snapshot of a localized wave packet. Why localized? Because the wave packet here, the localized, okay, it is localized because the spread of the wave packet is limited. This is x equal to 0 point, and you can see at x equal to 0 the wave is at the peak. This is actually the results from the single slit diffraction you can see in your previous classes. That is actually what has been done here. You can go to this equation. Yes, you can see that the wave function is a superposition of large number of plane waves whose wavelengths are varying from minus infinity to plus infinity. So all conditions are taken, all possibilities of superposition has been taken over here. So all plane waves are superposed means at x equal to 0 they will construct, they will interfere at every point in the space. So at x equal to 0 they will construct a constructive interference, that is the maxima will be there, and at later position x the secondary maxima will appear, but the secondary maxima has lesser amplitude than the principal maxima, which has formed at x equal to 0. So x equal to 0 the maxima is the central maxima or the principal maxima, and then at some point minima will appear, and then after some secondary maxima will appear also, but those are insignificant. So you can see here the problem was for free particle solution, that is the wave is traveling forever. So the position of the particle is uncertain, but here you can see the wave is effectively bounded into this region. So the position of the particle is uncertain, but by amount of, say, this is called the width of the wave function delta x, or the width of the spread. of the wave packet. So there is a finite width. So uncertainty is finite. Delta x is finite. So there is a finite uncertainty. If you use the superposition theorem and construct the Gaussian wave packet. Similarly, the same picture will be in the case of the momentum space wave function, because in the momentum space wave function psi tilde k, it is again a superposition of a large number of wave packets, and so psi k tilde is also like this. Okay, so at around k is equal to 0, and it has finite uncertainty. Here it is plot. What is plot? Psi tilde k is plot. So the psi tilde k has finite uncertainty. So it is consistent with the Heisenberg uncertainty principle, which have to be true all the time. And how you can measure those width, it is written over here. You can go through. There is the same policy as was taken in case of the forced vibration, the half power frequency. So this, and probability also, the probability is finite. Probability of finding the particle is also finite. So those problems are solved out. And another thing, the velocity of the particle. We have seen that if you take the plane wave solution only, then the velocity of the particle is equal to twice of the velocity of the wave, that is phase velocity of the wave. Okay, so phase velocity of the wave, but actually the particle is moving with the group velocity of the wave. It can be shown. So group velocity of the wave is the particle velocity. So the problem of the discrepancy of the velocities of the wave, which is moving slower than the particle, where we have used the dual nature, so both speeds should be consistent with each other. And yes, it is consistent because the particle velocity is the group velocity of the wave. So all ideas are conserved, and wave packet conception, that is the linear superposition of the plane wave solutions for the free particle, saves our life and saves all the theories, all the principles of quantum mechanics as well. So in my next lecture I will discuss the spread of the wave packet, and in my present lecture I have not discussed the shape of the wave packet, because the wave packet, the form of psi is not written over here. So the shape of the wave packet was very much general in our discuss, but as a special case we can think about the Gaussian wave packet, and for the Gaussian wave packet how the uncertainty principle holds, and what is the spread of the wave packet, that is how wave packet changes its shape and position with respect to time, we will discuss in our next class. So thank you for listening.